I think in the very first class, we have completed the concept of multiplication of matrices. And after that, we started discussing about the transpose of a matrix. Right? What is a symmetric matrix? What is Skew Symmetric Matrix? Orthogonal Matrix? And when it comes to the complex matrices, we have seen the Hermitian matrix. We have also seen the skew Hermitian matrix, unitary matrices. And I told these matrices, complex matrices, are not so important as far as the gate examination is concerned. We have also seen the LU decomposition of a particular matrix, how we do that. Right? And then we started discussing about the concept of determinant. The concept of determinant is very, very important as far as the gate examination is concerned. Because it not only helps you in the concept of determinant, but it also helps in the concept of eigenvalues and eigenvectors, which is one of the hot topics of the linear algebra, where mostly the question is going to come from. So the concept of determinant, its properties, I think in the last class we have learned about the properties of the determinant, right? What did we learn? First property is that if you interchange the rows or columns, if you interchange row and column, or row or column, right? In that case, the determinant is going to be multiplied by -1. The determinant is going to be multiplied by -1. Second, if any of the row or any of the column is multiplied by any scalar, the determinant of that matrix is also multiplied by the same scalar. Initially, without multiplying, if it is some delta, then after multiplying, it's going to become k delta. So if each and every row or a column is multiplied, in that case, the determinant that previously we had before multiplying is going to be multiplied with of k power n, where n is the order of the determinant. So order of determinant, we have learned that order of determinant is nothing but if you are having a square matrix of n cross n, then n is what we call as the order of the determinant. And the mandatory condition to calculate the determinant is that it should be a square matrix. Yes or no? It should be a square matrix. So again we have seen that when two rows are identical or two columns are identical or proportional in nature, the determinant is going to be equal to that of 0. Yes or no? In the case of a triangular matrix, in the case of a diagonal matrix, in both the cases, the determinant is nothing but the multiplication of principal diagonal elements. It is a multiplication of principal diagonal elements, right? So if you are having any particular row or a column which is an addition of two numbers, then it can be separated into two different determinants. The last property that we have learned is that by doing the elementary operations, row operations or column operations, the determinant is not going to change. Okay, one thing I want to make clear regarding the determinant is that whether you are going to use row operations, whether you are going to use column operations, whether you are going to do both, the determinant value is not going to change till you are following the operation that any particular row, let us say that I am operating on the row 1, it is going to be R1 plus K1 R2 or K2 R2, K3 R3 plus so on. And C1 dash is going to be C1 plus K2 C2, K3 C3 plus so on. Right? So these are nothing but the column operation and the row operation. In the last class, one of the student has asked regarding the inverse of the matrix. There to come in to ensure that okay, the matrix is going to become an identity matrix. We can use the row operations and column operations. Row operations, column operations are not going to change the determinant of the matrix except you are changing the coefficient of the row. For example, if I am operating on the row 1, I have to ensure that the coefficient of it is going to be remaining 1. If I am operating on the column 1, I have to ensure that its coefficient is going to remain 1 only. So this is the care that we have to take when we are applying the row operations and column operations. When we calculate the inverse using the elementary operations, then we also do a particular operation in order to ensure that the matrix A becomes an identity matrix. We will ensure that R1 is going to be something like R1 by 5, which is not a proper elementary operation or a proper row or column transformation. Because generally when you are applying row transformation or a column transformation, you have to ensure this condition is satisfied. If you are doing something like this, to convert any number into a unit number, then this is going to be considered as a wrong operation when you are using it to find the determinant. You can use it for finding the inverse, but you should not use this operation to find the determinant of the matrix. I'm sure that whatever doubt was there on the other day regarding the determinant, can we use the row operations, column operations, is cleared. So this is the row operation and column operation that we can use. We cannot have any other coefficient except 1 on the column or a row on which you are operating. So this is what we have discussed in the last class. Now we will go ahead. In today's class, we are going to discuss about the concept of determinant. We'll solve the problems. The concept has been more or less covered in the last class. We will complete solving the problems on determinant, and then we will come to the concept of inverse. As a prerequisite, we will be discussing about the concept of minors, cofactor, etc. Adjoint. After completing this, we will go into the concept of rank. This is what is going to be discussed today. Right, so these are the learning objectives for today's class. Let us see how much we can do for today's class. Right, so this is the question I told you to solve, but yes, we didn't discuss this problem. Right, I think many of you have answered in spite of that. I think you have answered it as option A, isn't it? Yes, option A is the right answer. Right, because if you observe, option C, option B and option D are nothing but you are applying the row operation or column operation, then you are going to have option B, option C and option D. Whereas, in the case of option A, to get the same matrix that is there on your board as option A, you have to apply the interchanging of columns. Then only you are going to have that particular thing. So you know that when you are interchanging the columns, definitely the determinant is going to change. Right? So let me do that. Let me do that. C3 dash is going to be equal to C3 plus C2. If I do this operation, so this is the operation that I have performed. The column 3 is going to be column 3 plus column 2. Many of you have answered the answer. Many of you have answered it as option A. I am explaining why it is so, right? So the very first column operation that I have performed is that the column 3 transformed is going to be equal to column 3 plus column 2, which is a valid column operation, isn't it? It is a valid column operation. Now one more operation I am going to perform is that C2 dash is going to be equal to C2 plus C1. So 1, 1, 1, x plus 1, y plus 1, z plus 1, x into x plus 1, y into y plus 1, z into z plus 1. Now you see, when I interchange the columns, 2 and column 3, then minus of, right, so you can see that whatever determinant you are having, it will be equal to minus of this one. So therefore option A is wrong because of the presence of minus sign. And option B, option C, option D are valid row and column operations which have been performed. So therefore all the determinants will be equal. Please go for the next problem. I'm sure that the video quality is fine. Please note on the problem. So there is a question that why option A is correct. It is because of the reason that you have to do this particular operation. I told you that whenever you are going to apply the column operations, whenever we are going to interchange the columns, the determinant is going to be multiplied by minus 1. That is the reason why we are taking a minus here. Because when I interchange it, the determinant of this will be equal to minus of this one. Now till now we have applied only the column operations which are genuine enough. Right, so therefore here the answer remains option A. The property number 1 is that when the rows or columns are interchanged, then the determinant is going to be multiplied by minus 1. That is not a column operation, that is not a row operation. It is an interchanging of the rows or interchanging of the columns, which is going to ensure that the determinant is going to be multiplied by minus 1. Right, so the answer for this particular question, I can see quite a few of you are answering it as option B. Can you please tell me why it is option B? Can I apply the operation on the row 1, that the row 1 is going to be equal to that of R1 plus R2 plus R3? Can I do this? R1 dash becomes R1 plus R2 plus R3. If I do this, then I'll have a plus B plus C, A plus B plus C, A plus B plus C. Please check this. We are just adding the row 1 with the row 2, row 3, and it is present in the row 1, which is again a valid row operation. So A minus B minus C plus 2B plus 2C is going to be A plus B plus C. Same here, same here. So A plus B plus C comes outside. A plus B plus C comes outside. So the determinant of A is divisible by A plus B plus C, which is true. Let us go for the next problem. Please note on the question and try to solve it. Students who have just joined, I don't think we have missed by much. It is only 1 or 2 problems. So first thing that I am going to do is that, see, the idea behind solving such problems which are of higher order is that we have to convert it into row echelon form. We have to convert it at least near to that of the row echelon form. For example, such a matrix, if I am able to convert it into like this, it means making the first, all the rows first element as 0. Then what happens is that the determinant is going to be this element multiplied by the determinant of this one. This particular element multiplied by the determinant of the 3 by 3 matrix. Or you can simplify it further. You can simplify it further, something like this. Now the determinant is going to be x multiplied by determinant of this, which is further going to be another x multiplied by determinant of this. Or if you want to go one step more ahead, you can have a pure row echelon form. This is the pure row echelon form where you can just multiply the principal diagonal elements. You can just multiply the principal diagonal elements. Now let us try to solve the problem. As you know, we want one element at the top, which is 1 at least, or near to the top 1, which can make the other row elements as zeros. For example, if you observe in this question, the first row is starting with 0. Using 0, I cannot make the remaining row first element as 0. Yes or no? If my top row first element is 0, I cannot use this particular row to make the remaining row first element as 0. So what I'm going to do is that I'm going to interchange the first and second rows. I'm going to interchange first and second rows. So what happens naturally is that when I interchange the rows, the determinant is going to be multiplied by minus. So I will have 1 0 3 0 0 1 2 3 2 3 0 1 3 0 1 2. Now you see what happens is that by this thing, this particular element has become 0, which is required for us. And let us make this element and this element also 0 by using the first row. The operation that I am going to perform is that R2 dash is going to be R2 minus 2R1. It means that R2 minus 2 times that of R1. 2 minus 2 is going to be 0. That is the idea of doing it. R3 dash is going to be R3 minus 3R1. R3 dash is going to be R3 minus 3 times that of R1. It becomes 3. 3 minus 3 is going to be 0. So I'm going to apply these two operations. So what it is going to become 1 0 3 0 0, 1, 2, 3, 0, this element becomes 3 only. Here you're going to have minus 6 and here you're going to have 1. 3 minus 3, 0, 0 here, 1 minus 9 is minus 8, 2 minus 0 is going to be 2, which is equal to that of 1 times that of determinant of this element, which is equal to 1 into minus 12 plus 8, which is minus 4, minus 2 into 6 plus 3 into minus 24, which is equal to minus 4, minus 12, minus 72, which is minus 88. And you know, here we haven't taken this minus into consideration. If I take this minus into consideration, minus of this one, it becomes plus 88. See, ultimately we have only done two operations here. First thing is that we have interchanged the rows, and second thing is that we made this element as 0. Now so that you are having only 3 by 3 matrix. See, you can further go ahead. I'm sorry. Yes, you are right that this should be R3 here and here it should be R4. This is my mistake. So basically we have operated on R3 and R4 because R2 already this element is 0, right? R2 already this element is 0, so it is not required to once again operate on the second row. So second row remains the same. This operation that we are performing is on the third row and fourth row. See, here we have ensured that these three elements are 0, and so that the determinant is going to be this element multiplied by this. Okay? So that now you are only having a 3 by 3 matrix. I can also further ensure that even these elements become 0. So that you're going to have 1 times it of 1 times it of. But for that we have to make this element 0. In the process of making this element 0, these elements will change. Okay, again Rohit, the same question. Is row operation not changing the determinant value? That is what is the property, right? If you are applying the row operation, if you are applying the column operation, the determinant is not going to change, provided you are ensuring that when you are applying the row transformation on any particular row, its coefficient is going to remain 1. Meanwhile, students, please go for the next question. It is a very simple question that has been asked in GATE 2014. Here you are having one column, here you are having one row. So we can call it as a column matrix, here we can call it as a row matrix. So when you multiply both of them, here we are having a single column, so it's going to be 3 cross 1, and here it is 1 cross 3. The resultant is going to be 3 cross 3. So we will have 2, 18, 10, minus 4, minus 36, minus 20, 7, 63, 35. If you observe, all these rows are nothing but proportional rows. All these rows are nothing but proportional rows. Yes or no? You can please check. What I can do is that, considering this as determinant, if I can remove 2 from the first row, then it becomes 195. If I can remove minus 4 from the second row, it becomes 195. If I remove 7 from the third row, then it again becomes 195. That is why I told you, whenever we are having the proportional rows or columns or identical rows, the determinant is going to be equal to the of 0. Right? So the answer is going to remain 0. Students who have completed, go for the next problem. Please, I think I already told you, the transpose of the matrix A will have the same determinant as that of the original matrix. So if I apply the transpose, A transpose, and then take the determinant, it will be equal to the determinant of A. The idea is that I'm going to take the transpose. So A2 0 0 0 5 0 0 3 1 2 0 7 3 4 B. So what you'll have here, A times that of 5 0 0 1 2 0 3 4 B minus 2 times that of 0 3 7 0 2 4 0 0 B. Right, so when I consider this particular element with a minus sign, I already told you when you take the determinant, first element with plus, second element with minus, third element with plus, fourth element if it is there, it is going to be with minus. And all the remaining elements, for example, if I am considering A here, then I will not consider this column and this row. I will only consider the remaining elements, deleting the row and column to which A belongs to. And when I am considering this particular element, I will again delete the column and row to which it belongs to. Now what happens here is that you already have a single row which is completely 0. So therefore this element becomes 0. Now it is A times that of, now you see which type of matrix it is. This is nothing but a lower triangular matrix. And in the case of a lower triangular matrix, the determinant is the multiplication of principal diagonal elements. So I haven't done much. So AB multiplied by 10 is what is the determinant of A, which is equal to the of 100 as given in the question, which implies that the value of AB is equal to the of 10. The value of AB is equal to the of 10. The trace of the matrix is given as 14. So what could be the trace of the matrix? A plus 5 plus 2 plus B. A plus 5 plus 2 plus B is the trace of the matrix and it is given as 14. In that case, the value of A plus B is equal to 7. So A plus B is 7 and AB is nothing but 10. So therefore, we can use these two to find out A minus B, because we know A minus B whole square is going to be A plus B whole square minus 4AB. So it is 49 minus 4 times the of AB, which is 10, which is equal to the of 9. So A minus B is equal to 3. Because the mod is given, it's going to be equal to the of 3. See, what is the trace of the matrix? This is something you have dealt in the first class. The trace is nothing but the addition of the principal diagonal elements. Can we make it by converting it into a triangular matrix? Yes, you can do that. But you have to ensure that the number of steps are lesser. Here what we have done, very simple thing, that we have taken the transpose of it and then try to expand it. Fortunately, this became 0. So directly here you are having a triangular matrix. So it is quite simple to solve this problem. The P matrix is given as alpha into J6 plus I. Yeah, I6 multiplied by I6 is nothing but identity matrix of order 6 plus alpha J6. So basically in the question it is given I6 plus alpha J6 or alpha J6 plus I6, both remain the same thing. Now when I add both of them, what happens? 1 0 0 0 0 alpha, 0 1 0 0 alpha 0 0 0 1 alpha 0 0 0 0 alpha 1 0 0 0 alpha 0 0 1 0 alpha 0 0 0 0 1. Now take the determinant and equate it to 0, because the question it is given that the determinant is equal to 0. So the determinant of P will be equal to 1 0 0 0 0 alpha 0 1 0 0 alpha 0 0 0 1 0 alpha 0 0 0 0 alpha 1 0 0 0 alpha 0 0 1 0 alpha 0 0 0 0 1. Okay, I am considering the determinant, equating it to 0. Now you see, there is a determinant which is equal to 0, which is already given. It means that some of the rows have to be identical or proportional or addition of some of the rows. Now very simple thing that comes to your mind is that it looks like the row 1 and row 6 are slightly identical if you observe carefully. If I ensure that the value of alpha is equal to 1 or the value of alpha is equal to minus 1, then what happens? You are having, if I take the value of alpha as 1, then it is 1 0 0 0 0 1. Here I am going to have 1 0 0 0 0 1. It means that the last row and the first row are identical. If I take the value of alpha is equal to 1, then definitely the value of determinant is going to be equal to 0. The second approach is that you take the value of alpha is equal to minus 1. So 1, 0, 0, 0, 0, minus 1. Here I'm going to have minus 1, 0, 0, 0, 0, 1. Now both of them are proportional. Both of them are proportional. In fact, what I can do is that I can bring minus outside from the last one. If I bring minus outside, then it's going to be 1, 0, 0, 0, 0, minus. If I bring the minus outside, then it's going to be 1, 0, 0, 0, 0, minus 1. Then both the rows are going to become identical in nature. So therefore, even for the value of alpha is equal to minus 1, the answer remains 0. So these are the two values of alpha that we can find out. No other value of alpha is going to satisfy. These are the two values of alpha. By comparison, we can come to know that the alpha value is going to be plus or minus 1. But in the question, it is given that alpha is a non-negative number. Alpha is a non-negative real number. It means that alpha cannot be negative. It means this possibility is removed. If this possibility is removed, there is only one option which can satisfy, which is the alpha is equal to 1. So the answer for the question is alpha is equal to 1. See, the reason why we are taking alpha is equal to 1 is because once the value of alpha is equal to 1, the first row and the last row are identical, the determinant becomes 0 because it's already given the determinant is 0. One of the possibilities is that the alpha is equal to 1. The other possibility is alpha is equal to minus 1. Rahul, can you please tell me what is the distributive rule? What is the meaning of that? See, when the value of alpha is minus 1, don't you think the first row and the last row are proportional to each other? 1 by minus 1 is equal to minus 1 by 1. Or, one more way is that bring minus outside from the last row. If you bring minus, if I consider the value of alpha to be minus 1, if I bring minus outside, then it's going to be 1, 0, 0, 0, minus 1, which is identical to the first one. Then also the determinant is going to be equal to 0 for the value of alpha is equal to minus 1. But minus 1 cannot be the answer for the fact that alpha is given as a non-negative real number. Please try to understand the question which is given here. It is already given that the matrix A and B are rectangular matrices. A, M cross N, N cross M. It indicates that both of them are rectangular matrices. Now, it is given a condition that identity matrix plus AB determinant is going to be equal to determinant of identity matrix plus BA, where I is a identity matrix. Using the above property, the determinant of the matrix given below is. So we have to write in the form of identity matrix plus AB. If I can write it as determinant of identity matrix, let me write identity matrix 1 0 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Identity matrix plus 1 1 1 1 1 1 1. Now you see it is something like identity matrix plus AB. Identity matrix plus AB. So I'm trying to use this particular principle to say that okay, identity matrix plus AB is given as identity matrix plus BA, where because I'm adding identity matrix of fourth order, I don't know the identity matrix of this because it all depends upon the order of BA. Right? So one thing is very clear, I can consider that AB is going to be all ones. See, when did we have all the rows are same or proportional? Do you remember? Just now in determinants we have solved a problem where we had all the rows are going to be proportional. When did we have that? When did we have all the rows are proportional to each other? We had that when we had a multiplication of the column matrix and the row matrix. If I consider the column matrix and row matrix something like this, 4 cross 1 and 1 cross 4, then I'm going to have a matrix something like this. AB, which is going to be something like this, is going to be equal to the top. True? So I can consider this is A, this is B. Now with the same reason, what will be BA? BA will be 1, 1, 1, 1, 1, 1, 1, 1. So here I'm going to have a 1 cross 4. Here it is a 4 cross 1. So therefore it will be 1 cross 1. The resultant matrix is going to be a 1 cross 1 matrix. So here the determinant of I into AB should be equal to determinant of I into BA. So here I have to take the identity matrix of 1 cross 1. So identity matrix of 1 cross 1 is nothing but 1 itself, plus BA will be 4, which is 5. So the question is framed in such a way that you have to use this property. I plus AB is equal to I plus BA. So from this I plus AB, we can understand all the rows are proportional, which can happen when you are having a column matrix and a row matrix. When we have a column matrix and a row matrix. So therefore, if I interchange that row matrix multiplied by the column matrix, now you can see that it's going to be a 1 cross 1 matrix. So using this particular property, which is given in the question, I plus BA, BA is a 1 cross 1 matrix, so identity matrix I've taken should also be a 1 cross 1 matrix. So from here I got the determinant to be equal to 5. Yeah, I'll explain once again. Let us see whether it is going to get clear or not. See, the question is focused on that we have to find the determinant of the matrix which is given. And the matrix is something like this. And one thing that has been given in the question is that we have to use the property that I plus AB will be equal to determinant of I plus BA. Our identity matrix that we are using in both of them, one is of order M, the other is of order N. Right? So A is going to be an M cross N matrix, B is going to be an N cross M matrix. So these things are already given in the question. Now what I'm doing, I'm trying to write just like the way he has asked in the question. He told we have to write it in the form of I plus AB. So I plus AB. So AB is going to be a 4 cross 4 matrix, isn't it? AB is going to be a 4 cross 4 matrix, 1, 1, 1, 1. Is there any other possibility of writing it? If I want to split it into identity matrix plus another matrix, this is the result I'm going to get, yes or no? Right? This is the result that we are going to get. So once we get this particular result, how can we have an AB which is going to be equal to all ones? It is possible when you are multiplying a column matrix and a row matrix. Right? So that's why I have considered a column matrix and a row matrix in such a way that I can have all the elements as 1. Now what is going to be BA? Row matrix multiplied by column matrix, which results in what? Which results in 4. It results in 4. So I'm using again the property I plus AB. I plus AB will be equal to I plus BA. BA is nothing but 4. So it is 4I multiplied by identity matrix of order 1. So therefore it is going to be 5. Why A is 1, 1, 1, 1? Is there any other way of writing? See, our aim is not that what we are taking. Our aim is that we have to get the AB values as 1, 1, 1, 1. And from the past experience, what we have learned is that we can have all the rows as proportional rows only when you take the column matrix multiplied by the row matrix. Then only you can ensure that all the rows are proportional. Why AB is 1, 1, 1, 1? It is because you have taken the column matrix multiplied by row matrix. Multiplication of all these things is what? See, the only difficulty that I can see in this problem is that converting a 4 cross 1 matrix, which is having all the rows same as that of a column matrix multiplied by a row matrix. This is probably the idea that generally not many people get. You have to understand one thing, that anytime you are having all the elements as same, it could be the multiplication of the column matrix multiplied by the row matrix. Once you understand it, getting this idea is not so difficult. That considering all the elements as ones. See, if still anyone has a problem regarding this particular question, you can definitely ask this question at the end of the class, right? I will repeat it as many times as you want. 3, 4, 45, 7, 9, 105, 13, 2, 195. This is how the particular matrix has been constructed. Now you see here the column 1 and column 3. Do you see any similarity between them? Do you see any similarity between them? Yes. The first column multiplied by 15. 3 into 15 is 45. 7 into 15 is 105. 13 into 15 is 195. So therefore, you can see there are two proportional rows that two proportional columns that we are having. So the determinant of this matrix, the determinant is going to be 0. Whenever we are having two identical rows, two identical rows in fact, or two identical columns, or proportional columns or proportional rows, the determinant is always going to be equal to the top 0. The determinant is always going to be equal to the top 0. So the answer is 0 for this matrix. But here what is told? First part of the question, perform the operations on the matrix. So the matrix has been given and we have to perform the operations. What is that? Add the third row to the second row. So second row is nothing but, this is the operation that we have performed. And the second operation we have to perform is to subtract the third column from the first column. Subtract third column from the first column. Do you think that the determinant is going to change when I apply these two operations? Do you think that the determinant is going to change when I apply these two operations? No, because these are the possible row and column operations that we can perform. And we know the property that the determinant is not going to change when you are applying these operations. So therefore the determinant remains 0. It was 0 before, even now it is going to remain 0. So the answer for this question is 0. Please understand how important and critical these properties are. We'll come to this question later when we discuss about the concept of eigenvalues. Let me quickly explain the previous problem. The Gagan is asking to repeat it once again. In the previous problem, we have observed that the first column and the third column are proportional columns. Once you multiply the first column with the third column with 15, then you will actually get the third column. Once we multiply the first column with 15, we will get the third column. Right? It means that first column and third column are proportional. Whenever it happens, the determinant is 0. The operations that have been recommended in the first part and the second part, the operations that have been recommended in the first and second part are nothing but the row operation and column operation. So we know that by row or column operations, the determinant is not going to change. So initial matrix that we had, determinant is 0. After applying the operations also, the determinant is going to remain 0. So the answer for this question is 0. So now here in this particular question, that we are given a triangular matrix. Which type of triangular matrix it is? Which type of triangular matrix is this? The matrix is a upper triangular matrix. But that doesn't matter. What we have to find here is the determinant of A inverse. Determinant of A inverse. It means we have to find the inverse of the matrix, which we didn't learn till now, and then apply the determinant. Instead of doing that, what we can do is that determinant of A inverse is nothing but I by A, which is going to be 1 by A. The determinant of A inverse is always going to be 1 by determinant of A. And we know it is a triangular matrix, so therefore determinant of A is nothing but a multiplication of principal diagonal elements. Yes or no? Because it's a triangular matrix, so directly the determinant is nothing but multiplication of the principal diagonal elements. See, we'll come to the concept of inverse straight after completing the concept of determinant. Don't bother about it. I'm telling the methods. First method is that find the inverse, then find determinant. Second is that using this particular property, that the determinant of inverse of the matrix is going to be 1 by determinant of the matrix. Right. So matrix A is nothing but a triangular matrix. So determinant is nothing but multiplication of principal diagonal elements. So the determinant of A is nothing but 4. So 1 by 4 is going to be the right answer.